Okay, can I start now?
Yeah.
Yeah, the recording is on now.
All right. So can you see my screen?
We see your screen and your laser.
Okay, great. So first of all, I'd like to thank the Thomas and Maxime for giving me a chance to talk about our recent work in CMDS webinar. Yeah, so then today I'd like to talk about the vibrational dynamics of interfacial water revealed by 2D heterodyne VSD spectroscopy. Actually, since the 2D spectroscopy started more than decades ago, I have been, a good audience for a long time, but because of this activity, now I can join 2D community. Now I'm very happy. Okay, so today what I talk about is, oops, just one, okay, sorry. Okay, so today I talk about the vibrational dynamics of interface. And as all audience of this webinar knows that out-of-phase dynamics in bulk has been extensively studied by advanced spectroscopy such as 2D IR and 2D ES. But knowledge about the molecule, the interface, in particular liquid interface, is very limited. So about the more than 15 years back, I had a quite naive dream that if we could raise the level of the spectroscopy at the interface to that for the solution, maybe we could see a lot of interesting stuff. That's the motivation of this this activity of our group. So the problem of the liquid interfaces, if we apply ordinary spectroscopy, what we can observe is the signal from bulk. And actually the interface molecule in this sense is just the molecule located in one or two monolayer at the interface. So then the signal is dominated by signal from bulk, so that we cannot see anything from the interface. So naturally, we need the spectroscopy which has the intrinsic sensitivity or selectivity of the interface. So as again in this committee, everybody knows that the second order nonlinear spectroscopy has intrinsic interface selectivity, because the second order nonlinear optical phenomena occurs only in the region where inversion symmetry is broken. So obviously, in the bulk region, a kind of water solution, and the air region has quasi, in practical sense, have symmetry, inversion symmetry, but the interface, inversion symmetry is broken. So that once we irradiate the infrared and the visible light, and if we observe the some frequency signal, we just say that signal comes from the interface. So by changing the infrared frequency, if we have the vibrational resonance, the intensity of some frequency signal is increased. In that way, we can selectively observe vibration spectrum in molecular interface. This is some frequency generation spectroscopy. And it was nice spectroscopy which started by Ronshen in early 90s. Well, around the 2000, the people came to understand that this spectroscopy has intrinsic problem. The reason is the ordinary second order some frequency spectroscopy, it observe the intensity of some frequency signal directly. So it means that the molecular response with susceptibility, which we call chi2, is proportional to the electric field, not intensity. And the intensity signal is proportional to the square of the susceptibility, meaning that meaning that what we observe the spectra of the chi2 square. So then, meaning that we lost a lot of information, and the spectrum is distorted. So in order to solve this problem, the heterodetection detection is important, in which we introduce local oscillator from somewhere, which is another femtosecond pulses, and overlap with signal generated from interface is a phase controlled way. So then actually this is the low spectrum we obtain, and we observe this kind of fringe which comes from the interference between local oscillator signal, and the phase of this fringe provide us information of phase of the electric field with a signal, and amplitude provide us information about the amplitude of the electric field. So in this way, we obtain the spectrum imaginary chi2 itself. Then this is a typical example, the VSC spectroscopy. This spectrum is very famous spectrum of the air-water interface reported by Ronshen in 1993. And in addition to hydrogen bonded OH Broad one, we observe very sharp free OH bands. So everyone is astonished, was astonished because at the interface we expect the OH bond which is stick in the out of air, out to the air. So actually this is free from the hydrogen bond. So that is very sharp. So this spectrum itself, the manifests the importance of this interface selective spectroscopy. And this is a typical spectrum of the obtained with the heterodyne detection, which is imaginary chi2 spectrum. So in this case, spectral distortion does not exist, and in addition to that, imaginary chi2 spectrum has the information sign. That the free OH appear with positive sign, which corresponds to the free OH has the H up orientation, but hydrogen bonded OH appear with negative sign, which means that the hydrogen bonded OH has H down orientation. So this heterodyne VSG spectroscopy provide imaginary chi2 spectrum, which are not the chi2 square spectrum. And imaginary chi2 spectra can be directly compared with linear absorption spectra bulk. The actually infrared absorption spectra corresponds to vibrational resonant imaginary chi1 spectrum, and Raman scattering vibrational resonant imaginary chi3 spectrum. And the chi2 signal appear with sign reflecting the absolute orientation of the molecule. So then after using this spectroscopy for a long time, I think that the most important issue is the additivity of the spectral component. So it means that the imaginary chi2 spectrum can be decomposed the component spectrum if the spectrum consists of the several components. So it means we can spectral decomposition. So in linear spectrum or infrared Raman, it is straightforward, but in the case of the interface selector spectroscopy, it's not trivial issue, because what we observe the chi2 square spectrum. In this case, we cannot decompose the spectral component to spectrum, obtain spectrum to the component spectrum. This is very big issue. All right, so then we have used this, technique to the steady state, to study steady state property of interfacial molecule. We observe free OH, other things, but of course interface is dynamic. So then we started time resolved heterodyne VSG spectroscopy. So again, the heterodyne detection is very crucial. Even though we can carry out the time resolved homodyne VSG spectroscopy, what we observe the pump induced difference of chi2 square spectrum. It means even though we observe nice spectrum, what we obtain this quantity, it's almost impossible to analyze this spectrum. But in the case of heterodyne detection, what we observe is just pump-induced imaginary chi2, which can be directly compared to the time resolved infrared or time resolved Raman. So then this is a setup for time resolution heterodynamic VSFG or 2D heterodynamic VSFG. And actually we irradiate the infrared pulse, which is a little bit narrowed for selective excitation, some portion of the bands, and we introduce the omega-1 narrow bands and broadband infrared. And first we introduce the these two pulses, the quartz, to generate local oscillator, and the omega-1 and omega-2 and local oscillator is focused on the sample where the signal is generated. Then a local oscillator signal generate the interface is introduced this polychromator in collinear way. Then in the polychromator, these two pulses, the interference and give the fringe. So then to get the 2D heterodynamic spectrum, we change the narrow band omega pulse and measure the times of the spectrum. Then we produce the 2D heterodynamic VSFG as the original Peter did for 2D spectroscopy. All right, so then as an example, first I show the older data about the positively charged the surfactant interface. So this is the CTAV. We have monolayer on the water surface, and this is the OH stretching region, and with the CH stretch bands. And in this interface, the charge is positive. So water is oriented with H down because the water is not happy to orient the slightly positive water toward the positive surface. Then OH stretch band appear with negative sign. So then this is the 2D spectrum obtained from this positive charged surfactant interface. And it appear with sign, in this case, breach lobe appear with positive sign because the steady state signal is negative. This is only difference from the 2D IL. But we observe initially, elongation, then with the spectral diffusion, diagonally elongated, the breach becomes the round, reflecting spectral diffusion. So this is the spectrum obtained with the isotopically diluted water in which HOD is the main species providing OH stretching band. So use of this isotopic dilution is very important for 2D heterodynamic spectroscopy for water surface. The reason is this is the same CTA water interface, but from the neat water. You can see the times that we have very peculiar feature. Actually, it comes from the film resonance. So then, in order to obtain pure information from the about the structure and dynamics from interface, in addition to the heterodynamic detection, using the isotopic diluted water is very important. So that in this work, this presentation, I will show only the data taken from the HOD interface. All right. So then, actually this feature is corresponds to the feature which has been long believed as the ice-like water at the surface, but it's not due to the ice-like water because it's born in when we use the isotopic dilution. All right, so then we use the HOD where we have only OH for this 2D spectroscopy. So then we can suppress the intramolar coupling like a film resonance or symmetric anti-symmetric vibration. So then spectrum becomes very straightforward. All right, so then first I will explain the lipid water interface results. And actually, we interested biological system recently, and the cell membrane is actually the lipid bilayer. So then people are very much interested in the water property of this biological membrane. But I mean, it's not easy to directly study the water at such kind of biological membrane, so that we make the lipid monolayer on the water surface and apply the heterodyne to, time heterodyne VSFG. So first I will show about the data of the DPPG and DPTAP. The head group, just focus on the head group. DPPG has a phosphate having negative charge, and DPTAP has the choline, which has a positive charge. So then reflecting the difference of the charge, the DPPG shows the positive OH stretching bands corresponds to the H-up orientation of the interfacial water, and the DPTAP shows negative band corresponds to the H-down orientation, right? So then this is steady state. Then first I show the data of DPPG, and this is the time origin to the spectrum. We have bridge signal and the hot bands. And you can see the bridge lobe immediately after photo excitation perfectly diagonally tilted, indicating inhomogeneity in the OH bands. And then that the diagonal elongation becomes long, reflecting the spectral diffusion. And in the case of the positively charged the DPPG case, the we observe this diagonal elongation, but more vertical, you can see. So then and this the diagonal elongation again become the vertical, reflecting the spectral diffusion. And if we compare these two spectrum time origin, and most significant difference is the tilt angle of this, the bridge lobe. This difference is very significant, and actually spectral diffusion time is almost the same. And then the reason is readily understood by learning the knowledge obtained the 2D IR for water. And this is the correlation function of the hydrogen bonded in the bulk, which this paper is taken from the Andres paper. And it is known that the correlation of the hydrogen bond in the bulk water decays in the bimodal way. They have very fast decay on time scale 60 femtosecond due to the fast fluctuation. And then, which is followed by slow decay, which is 1.4 picosecond, which due to the hydrogen bond reorientation like this. And fortunately, our time resolution is not so high. It's about 200 femtosecond, so that we cannot catch this fast component. So it means that this difference is the difference of amplitude of the fast component at two interface, which means that in the case of DPPG, we have phosphate here, and the H-up interfacial water has strong hydrogen bond, which suppress very fast the hydrogen bond fluctuation, results in the almost perfectly the diagonally elongated the bridge lobe. But in the DP-TAP case, the choline cannot have hydrogen bond with interfacial water, so the fluctuation is very fast. Then the correlation loss in very rapidly. Then what we observe is the quite the vertical like the central line slope at the time zero. Right. So then next is what happened is sweet ionic lipid. This is phosphorus choline, in which we have both the head group with phosphate and chlorine. The first, we studied this system with steady state, and this is always stretching band, and this is again CH. And if we compare this spectrum with the, you can see directly, soon you can notice that this wedge band is basically positive, which corresponds to HF orientation. But if you compare with the DPPC, which have the phosphate only, the spectral OH stretch band is a little different. It is a little bit suppressed, and actually here we have kind of the bump feature. Then with several the spectrum, control experiment, we conclude that actually this component, missing component, spectral components corresponds to the wood, edge down orientation around the chlorine group. So actually, we were sure, but after that we had a controversy, meaning that two MD simulation was reported. One group, actually, the author is our group, is our friend, and claimed that they produced the edge up and edge down orientation of the water at the phosphogyl water interface. But another simulation say that they cannot find the edge down water around the chlorine. Then we have to do something. Then we carry out time zone measurements. And first I showed the one-dimensional time zone spectrum. This is a steady state spectrum, and we excite the pulse here, right? Then immediately after excitation, we expect the negative breach in this region, but in this region, we also observe positive breach, meaning that this positive peak is not just, consists of just one positive peak. It consists of the positive peak and negative peak. Oh, then, then spectral diffusion occurs, then this small feature is washed out by this much larger negative bands. So this positive feature appear at the time zero, corresponds to the small amount of the edge down orientation of water around the chlorine. So then, this is time zero spectrum. Certainly around time zero, we have the opposite, the breach lobe having opposite sign, which corresponds to the water around the chlorine, in addition to the major breach signal arising from the edge up orientation around the phosphate. Then spectral diffusion occurs in this time scale. All right, then now we can compare the three 2D spectrum of the lipid interface. One is DPPG, DPPC, DPTAP. I would like to talk about here the difference is the tilt angle of the initial breach lobe. This is almost the perfectly diary elongated. So it means a fast fluctuation of the water is suppressed. But even though phosphate exists in DPPC, but that the tilt angle becomes very small, meaning it's almost vertical. Meaning that in this case, even though the water has the interaction of phosphate, we have the fast refractuation water around the chlorine, so which affects the water around the phosphate, then the water fluctuation becomes much faster. So then DP-TAP, of course, the water cannot have hydrogen bonding, so that the fast fluctuation makes the tilt angle looks much more vertical. Okay, so this is the results, a little bit old results about the repeat water interface. But lastly, in the last 10 minutes or something, I would like to talk about more recent data about water, the charge hydrophobic water interface. And the hydrophobic interface, water interface, important. In short, it's a kind of water oil interface. The actually hydrophobic interaction is very important in not only chemistry but biology. So then we use the two types of charge, the hydrophobic molecule. One is tetraphenyl borate ion TPB minus, and actually it has boron at the center having negative sign, and which is surrounded by 4 aromatic group. The other molecule is the tetraphenyl aerosonium ion TPA, and at the center it has positive sign, but again this positive sign is surrounded by 4 phenyl. The phenyl is certainly very hydrophobic. So then we study the water at this positively negatively charged hydrophobic interface. All right, so this is a steady state heterodyne VSG data, and now you are used to it that in the case of TPB, it has negative charge. So then interfacial water has H-up orientation, so that we have positively OH bands. And in the case of TPM plus, because this is the surface, water surface is positive charge, the interfacial water has H down orientation, resulting in the negative DOH bands, right? So, but apart from this difference of sign, these two spectrum, steady state spectrum, looks almost similar. And if we compare these spectrum with the bulk HOD spectrum, measured with IR, these green curve, dot the curve, we change the sign, but more or less the same, although we can recognize a little bit broadening for TPB. However, we can observe interesting in dynamics. So this is the 2D heterodyne VSG spectrum of TPB minus. So immediately photoexcitation, it again nicely diagonally elongated, showing this OH stretch band is inhomogeneously broadened. Then spectral diffusion occurs on this femtosecond time scale, and here now you can see the single row start separating into two. So here you can see, isolated the peak in very high, frequency region. So it means that this dynamics 2D spectrum clearly shows the existence of the energetically isolated OH bond in high frequency region in the case of the negatively charged TPBA water interface. Okay, but in contrast, in the case of positively TPA plus water interface, yeah, again, we have nicely, diagonally elongated the bridge, and it shows the spectral diffusion, but energetically isolated OH signature never appear. So steady state spectrum looks almost the same, but the 2D spectrum shows very, significant difference. Then, actually, in the case of TPB minus, the water interface, we think that we assign it the isolated, energetically isolated water is OH bond having the pi hydrogen bonding with the aromatic ring of the negatively charged water, ion. So in fact, the pi hydrogen bonding has been reported and has been observed in infrared spectroscopy in argon matrix, and then a supersonic jet beam by rotational spectroscopy. And recently, by using Raman MCR analysis, even in the bulk, the pi hydrogen bond and the OH has been found. So that we assign that the identically isolated OH is the OH interact with the aromatic ring of the negatively charged hydrophilic ion at the interface. Of course, in the case of TPPA, water have H down orientation. Certainly, with this configuration, OH cannot form effectively the pi hydrogen bonding. So that this is the reason that at the PPA plus water interface, we don't have the energetically isolated OH frequency at high frequency region. So actually the water structure at the two charged hydrophobic interface, the sign of the charge at hydrophobic interface governs the structure and dynamics of interfacial water. That the sign of charge at the interface is an issue. So although steady state spectrum cannot provide a clear view about such kind of difference, but 2D heterodynamic VHD spectroscopy provide this kind of new insight. Right. So this is a take-home message. This is a summary of the what we have done with the 2D heterodynamic VSFG. So now infrared excited time resolved heterodynamic VSFG and 2D heterodynamic VSFG enable us to study ultra-fast vibration dynamics at the interface as we study ultra-fast dynamics in the bulk by 2D IR. All right. So lastly, I'd like to show my collaborator. So I actually, under this pandemic, we need to take the group photo by using Zoom like this, as every group is doing. And we have 3 groups in our lab, but in particular, these 3 parts, young people contribute to the 2D heterodynamic VSD work. And Ahmed has done the most recent work, and Inoue and the Shin did the work about the repeat. And Nihon is group leader of the interface group, and I started with him time resolved the VSG spectroscopy, and Yamaguchi was ex-group leader of our group. He is now full professor in Saitama University. I started all the interface business with him at Riken. So thank you very much for your attention.
Thank you very much, Tahei. So the talk is open for questions. Just put up your hand, raise your hand, and we will promote you to panelist if you have a question. So maybe while other people are still thinking, I have a question regarding the interpretation with respect to Fermi resonance. So are you sure that it's Fermi resonance and not symmetric and antisymmetric stretch vibrations that play a role there?
Okay, can
I forgot. I think this has been discussed a lot of times in the past.
Yeah, okay, so yeah, can I share screen again?
I think so.
Yeah. So this is quite this is great question, and actually we analyze we analyze the HOD spectrum quantitatively, and you can see the separation of the 2 bands appear mainly here, not here. So then we nicely explain this feature, and actually the broad hydrogen bond has inhomogeneous boson. When the portion which has nice resonance with, say, overtone, the bending, nicely split. But when the frequency, untapped free OH is the deviate from that frequency, the splitting becomes smaller. So in this way, we can nicely observe this appearance of the double peak. So then we believe that this is due to the film resonance. If it's due to the story, symmetric and symmetric, I think regardless of the position of the untapped the OH is OH bond should be split, more or less equal, and in same way. This is the, I believe, the answer to your question.
Okay.
But then, if I can take over from Thomas, so the bending mode is at 1640 wave numbers. Okay, so you double that, you end up with, let's say, 3200, right? Minus enharmonicity.
Yeah. Okay.
There is resonant with another mode.
Meaning?
Well, with the mode that is...
Okay, but yeah, okay. But actually, bending frequency at the water interface is now a big issue.
Okay.
So yeah, so it's an issue of the debate in the interface community. So yeah, okay, but yeah, basically, yeah, okay, I understand your points, but at least with the view of the symmetric and anti-symmetric, I don't think we can explain this 2D spectral future nicely. Maybe you can do it, but we cannot do it.
Well, I might sound quite here bold, but from this wonderful spectra, I would say, well, there are two modes. Okay, one is at 3200, another is at 3400, right? And then as the time progresses, the 3400 wave number relaxes down to the 32.
I like this. Okay, sorry.
Yeah, so that would be my reading.
Okay, right. Okay. Oh, come on. Okay, so yeah.
Okay, good. So right. Who would like to ask the next question?
So I think Ahmed Uysal has a question.
Yeah, please.
Thank you for the beautiful talk. My question is about the last part of your presentation at the oil-water interface.
Last part, new one. Yes, this is my first time for me to talk. Yeah.
So how different it is from the air-water interface in terms of like the heterodyne detected studies and also time result or 2D IR studies, like technically, what are the challenges and differences?
Okay, so actually the L, we continue to making effort to get the nice spectrum of the air-water interface, but air-water interface is extremely difficult. The reason is, today we discuss about only charged interface, right? The charged interface means that water is more oriented. So then in the air-water interface, there is no charge. So that is oriented, but the orientation, occurs only first or two monolayer. But in the case of charged interface, because of the electric field, the layer is a little bit longer, not so huge, so that the signal becomes much stronger than air-water interface. So in a sense, the obtaining nice 2D spectrum from the charged interface is easier than neutral air-water interface. Is it okay?
Yes, but how about oil-water interface? Like this last part, are these like, is it still air on the top or do you have oil?
No, we have air, air, and we have almost monolayer of this aromatic ion.
Okay.
This is more, yeah. So actually the oil-water interface or solid water interface is so-called buried interface. So it is challenging. We are now making challenging, but it's extremely difficult because it means that we have to control the phase of the femtosecond light through such kind of thick material. So if we have the air on one side, air is almost nothing. So then we can nicely control the phase of the femtosecond pulse, so that we can carry out the heterodyne detection.
Thank you.
So it's my dream to do nice heterodyne experiment for liquid interface, but we need to solve the many technical questions before success.
A short remark that I would like to make. Could you please go back to slide number 34? So that's just the one that was discussed. 34.
34.
34. Yes, this one. Okay. Yes, I would like to say very cool data. I like very much, okay, how what appears to be a kind of elongated peak at 0 picoseconds. Okay, so you can clearly see as you wait, it splits into 2 peaks. Okay, and that is because of this inhomogeneity that removed. Okay, so the peak becomes more, let's say, round shape. Well, it's not actually round here, but let's say round shape, and then you can clearly see the second peak over there.
Yeah,
that's really cool, and that well shows one of the powers of the two-dimensional spectroscopy.
Yeah, very much so. So yeah. So then after seeing this certain, of course, I'm big fan. I have been big fan of 2D, but after this one, I mean, 2D heterodyne is also very powerful interface problem.
Okay, good. Do we have more questions?
Yeah, I've got a question.
You always have questions, Paul. Right, please go ahead.
Hi, Paul.
Hi, Tahei. Really fascinating talk. Two questions. One is about the thermalization, and you're on the right slide here. So
yeah.
At 1.5 picoseconds, you have a positive feature appear there.
Yeah.
So it got me wondering, is that a thermalization effect? And then that got me wondering, do the thermalization effects enter at the interface slightly differently to the bulk? I mean, it's always a problem with these measurements that eventually you have a hot ground state.
Yeah.
And in your experience of all these different systems, is it different at an interface, the thermalization? So that's my first question. And the second question is a very simple one. Can you look at the decay of the anisotropy in these kinds of experiments?
Okay,
with
good.
Perpendicular pump and probe.
Okay, so for actually first question is more easy to answer. The thermalization is the issue. So then after if the thermalization occurs, so then the thermalized signal wash up the interesting spectral feature also at the interface. But I mean actually using the HOD, it seems the thermalization time becomes a little bit slower. But I mean, basically what we observe is the dynamics within 1 picosecond.
That would appear a bit faster than the bulk, yes?
Actually, I've never done the 2D IR for the bulk, so I mean we need to discuss with you guys.
Paul, in the bulk, it would be something like faster than 0.5 picosecond, as compared to 1.5 picosecond for HDO.
So about 10%. It's about 10%.
Because of resonances, right? So this Fermi resonance with the bending mode, okay, makes a very fast relaxation channel, okay, and as soon as you get rid of these whatever 3400 wave numbers, okay, energy, you split it down, okay, then it's much easier to
I'd focus on the isotope diluted case.
Yes.
Yeah. So in this case, isotope diluted, solution allows us to observe a little bit longer time in this sense. So for the anisotropy measurements, the anisotropy measurements is quite interesting. So we are planning to do that. But difficulty of the measurements at the interface is we can in a sense in the case of bulk we have magic angle, for example, and the initial depolarization is usually is 0.4. But actually, the interface is not three-dimensionally. Free rotation cannot be assumed. So then we need to implement the special theoretical treatments to analyze the anisotropy at the interface, which makes the situations more difficult. Certainly, we are interested in, but I mean, before challenging the more difficult anisotropy and polarization measurements, at the moment we spend more time on this kind of easy experiment.
Mm-hmm. Thanks, Tahei.
I was just thinking that then in this experiment, okay, can you simply look at the anisotropy by titrating the polarization of your heterodyne beam, right? Because then you can interfere with either of the polarizations of your signal.
Yeah, but actually the interface, the PPP and SSP and other things that provide the different tensor elements at the interface. So which makes the analysis very complicated.
Okay, I see.
Of course, I don't think it's impossible, but I mean, it's at the moment we are playing with the easier problem in a sense.
Could you just take the experimental approach of looking to see if there's a difference in the decay of the signals?
Yeah. So in a sense, what I said is compared with bulk, the interface phenomena, in particular dynamics, has not been studied well. So then there is lots of the unsolved and even untouched problem. So that's what I want to stress. Does it make sense?
Yeah. Yes, very much.
Okay, I think that in view of time, okay, we are should thank Tahei again. Okay, thank you very much. So I am now switching off the recording to